Okay, good morning everybody. Thanks for being here as always. Just going to make a few adjustments. You don't really need to see much of me, but just so you know that I'm actually here. And we'll do that. Alright, so have the gain down. Morning Brooksy. Morning Vince. Thanks for being here. Morning. Okay, so we're doing lab 10. Morning Daisuke. Doing lab 10 today, and you may have noticed that at this stage of the semester we're now kind of, the way it's set up to work is that and this is how it would have worked in the normal class, we would work through some of the lab content together. In fact, a lot of it in this class at this point of the semester. And then you'll get some homework questions that will sort of come back and reinforce some of the things that I've exposed you to. So that's a little bit different than we did it earlier in the semester when we were still trying to build sort of a foundation of basic information. And now that we're moving on to more complex things, I'm sort of exposing you to the concepts first through a lab, and then I'm having you go do some follow-up work with the homework. So that's sort of what change you're experiencing in terms of the way the content is being delivered. So I'm going to tell you what I'm about to do is set up the circuit for this lab. So let me go show you the diagram real quick. So I'm about to wire my circuit. From what I can see, the colors, the colors come through funny, and I don't really care to mess with it that much, but I'm gonna use green ones. So I'm gonna wire up 8 green LEDs, and then it looks like blue on the camera, but I'm gonna put a red one there. You can use blue, it doesn't really matter. It also doesn't matter if you use all green ones or a mix of colors. My own sense of order is pleased by using green ones in this case. So I'm about to wire this up. All I'm really doing is adding to the lab 9. So I'm going to switch out some colors from lab 9 and then add a few more LEDs is all I'm going to do. I've disconnected it from the board for now. So I'll go make those connections after I change out the LEDs. So I have, I'm going to use 8 green LEDs and 1 red LED. And then I have my, you can see that, 220 ohm resistors, just like we've been using. So there's not a whole lot of wiring work to be done here, but I'm going to do it on camera just to give you a chance to ask questions if something different looking to you happens. So that's what I'm about to do, and then we'll go work in the software part. So first thing I'm going to do is connect up 8 LEDs and a red, even though on the screen it looks like a blue. I'm going to use a red one. And then I'll have, and again, I've already got 5 of them going, so I'm just going to switch out those colors first and then add 3 new, wait, 1, 2, 3, yeah. I'm going to add 4 new ones, so I'll have 9 total LEDs when I'm done. So first thing I'm going to do is pull out these old red and blue ones that I was using and replace them with green ones because I think it'll look pretty to do that. So I'm bending my LEDs at the knee, and then just making sure that I get these plugged back into the right ports. But I'm not going to spend a whole lot of your time on this, just so you know that's what I'm doing. I'm making sure that the long leg goes back on the row with the resistor on it. And then I'm going to have to add some wires here in a bit. The wires, I don't have enough of one color of the wires to do anything about having a mix of colors, but at least my display LEDs can all be one color, which pleases me. You can experiment with this though. It's not going to change what what the output means. I'm not particularly hurrying, by the way. I'm just not going to stop a whole lot because you've seen me do this before. So there's 4 of them. Those are all greens. They look sickly on the camera, but they're green in life. And I'm just being careful again that I get the legs the right direction and that they're in the right row. I'm double checking that. Seems okay. Now I'm just going to keep going. So, new green one. And then, so that's a brand new light. So I'm going to do the resistor and the ground wire and the power wire while I'm on this one. So need to pull out some more resistors. This is the part that I struggle with the most because these are hard to get pushed into the breadboard. So I did the resistor and the ground wire for this new LED. Now I'm going to get a longer wire for the one that connects to the Nucleo board. Because it makes life easier if you have a little bit of maneuverability with the wire that goes to the board. And again, that one connects to where the resistor comes out. So I'm not going to connect it yet. I'm just all loose for now. This is my ground wire, which I'm probably going to pull out and move down to the end just to get it out of the way. All right, so what do I have now? 1, 2, 3, 4, 5, 6. So I got 3 more to go. 8 green ones on this lab. That's the main part of the display. Is the green LEDs. So what we're doing on this lab is we're actually creating a binary display. So we're gonna read a value in memory while the program's running, and then we're going to display that value. It'll be only 8-bit value, but we'll display that value as binary on our board. So the value 1, for example, on our board will have 1 of the green lights lit. You'll see that in just a second. Okay, so resistor. My least favorite part, the resistor. Probably that's in there. And then the one going to the board again, I'm just leaving all those loose, so I'm not even using my Nucleo board right now. Even though the wires are trying to catch it. Okay, so I'm not even on the Nucleo board yet. All right, last of the green ones. Remember, all these resistors are 220 ohm. So don't just randomly pick resistors. For some reason, people historically want to do that. Just pick random resistors, but they are not all the same. So make sure you're getting 220s. Ground wire. and then lead. I'm just looking for longer ones here. That one seems pretty long. Okay, so that should be 1, 2, 3, 4, 5, 6, 7, 8. That's 8 green ones, and now I'm going to go back and put one of my red ones that I was using here at the top end. Having trouble getting that one in, so I just got to be patient. Or try a different LED. I couldn't get that one in, so I gave up on it. Alright, that one cooperated with me. Still a 220 ohm LED. Seems fairly short. Oh, that one's broken. Whoa, there's a nice long one. It's broken also. Okay. So that's all wired up. We're going to be using this same circuit for a while. So if you can leave it be, you'll save yourself some trouble down the road. Okay, and I reattached a ground wire down here. So everybody, all 9 of those lights are on this ground. And then I have the ground wire here at the end. The diagram, it doesn't really matter, but I've turned it over because it's going to be prettier, I think, or at least it'll make more sense to you on camera if I have it facing this direction with the red light on the end over here. Okay, so now the wiring part. So I'm going to leave the ground for last. That's the easy one. But the red light, which looks blue on your camera, but that furthest one, I'm going to work from that end down the other direction. So that one goes to PB6. PB6. Oh wait, not PB6, D10 on the board. Remember, the D part is where it goes on the board. So D10 is where the red one goes. Get that. It's not going to help you a whole lot, but that one, which looks blue, but it's actually red on my desk. That one goes to D10. Then I'm going to do the first green one right next to that. What looks blue to you, that goes to D13. So next one over goes to D13. Notice these are, it's kind of be a jumble. Then D12. So I'll find the next lead. D12. I'm kind of double checking as I go to make sure I'm grabbing the right wire. So D12. Let's see. So I'm on the, I did the red one. I did the D13, I did the D12, now I need to do the D11, and I'm just being careful again that I'm actually grabbing the correct wire because it's starting to be a mess in here. So I will just kind of shuffle these. All right, D11, which is going to have to be crammed in there. Maybe. Okay, got it. D11. So there's a whole bunch crammed right in together right there. D11. What's this next one go to? D7. D8 is the next one. D15. Where's that one? That one's way up here. So D15 was way up here. D14 is right next to it. And then the last one goes to D6. So be careful about that. It feels like the wires are going all over the place on the Nucleo board here. But the reason why they're in that order is because it makes the programming part a little bit easy. So it just kind of, for whatever reason, the people who designed and built this board have designed it so that the internal mapping to these outputs doesn't sort of match perfectly to the hardware mapping, if that makes any sense. So if you notice, so the red light is PB6, that's the internal mapping, but then it goes A5, PA5, PA6, PA7, PA8, PA9, those are all in order, and then B8, PB8, PB9, PB10. So the reason why the hardware wiring is all a jumble is because we're trying to keep the internal mappings sort of sequenced more conveniently. It's easier to program A5, A6, A7, A8, A9 in order and then mess with the wiring that's D13 and D7 and all over the place than vice versa. Okay, so I need to connect ground still. And I'm going to go on the far side because this is getting too crowded for me to get my fingers in. Okay, so now I've got ground in there. So the first thing that, and probably not all of you are all wired up, but you can catch up to this later after you get the software in. But let's look at the software component. And for the next couple weeks or next few weeks, I don't think we have to change anything in the circuit. So we'll just get right into it in the future. But today, some of you may still be doing a little bit of wiring. But everything will be in video, so that's all right. So what I'm going to do, which is what I always do first, is I just make sure that all the lights can be turned on. And I'm going to do that in software. So I'm going to hide the browser and I'm going to go into software. So there's a big change this week. Is that we're not just using GPIO A bank anymore. We're actually using GPIO B bank as well. So I left these as blanks, but I'm going to go grab those values and I'll show you where I'm finding them, the easy place to find them. So part number one is to get the hardware address of the B mode register. So we're sort of graduating a step up. We're not only just using the A general purpose input output registers. Now we're using the B pins. And that's so we can do more LEDs. I'm seeing some lag. Hopefully it's not really affecting your experience too badly. So we need to go get these two values, and I'll show you where it's easiest to get those values. If you go to my website, and go to the file section, the easiest place by far to find this stuff is typically this ARM parallel IO document right here. Kind of simplifies things. So let's go use that to hunt down these values that we need, which is what is the hardware address of GPIOB mode, and what is the hardware address of GPIOB output? That's mode register, output data register for B. We've already been given A. Let's go grab B. Okay, so scrolling down. There are other places to find this. I just happen to find this document to be one of the easier ones to find this stuff in. Okay, so here we are. Here's the B bank. It starts at 40020400. So I'm going to grab that value and I'm going to plug it in. Now we're not finished with that, but let's go plug that value in. 40020400. So you know where I got those from. I just plugged them into the code here. Now we're not quite done because this value is called the base address. You can kind of think of the B section as being an array of registers. So in that array, we need two specific registers. We need the mode section and the ODR section, or register. So now I'm flipping back and forth. When you watch the video, you can pause. So if you notice on this document, all this is telling me really is where does the B array begin. And then I need to go look for the index values or the offsets to the pieces I want specifically. So the mode section, the offset is 0, 0. So for the mode one, I can just leave it B. That's exactly what I want. Now for the output one, it says the offset is 14, 0x14. So in code, I go to the output one and I change those last two digits to 14, and that locates it at the right spot in the B section, in the B array of GPIO. You might notice, by the way, if you look up at the A ones, the A mode offset was 0, and the A section output was 14, so the same offset. But notice it's not at 0400, it's at 0000. So this is a different array of registers than the B section. So now that we have those addresses, we can configure and then do outputs on GPIO-B. Okay, so what I'm looking for now is the things that I know have to be done to test my circuit. And what I want to do to test my circuit is fire up all the LEDs at once. Hopefully I left it where you're still looking at code. Okay. So I'm just going to go down and look for the numbered elements until I get to something that's hard. Okay, so enabling the clocks. So the clocks, the clock bits look like DCBA, and then there's more. But all I'm really interested in is A and B. So I need to turn on the A and turn on the B for the clock bits. Now, all of this code right here is one section. So I get the address of the clock enabler in R3, and then I get the current value of the clock enable. The value is now in R2. So what I want to go do is update the value in R2 to make sure that the clocks on A and B are both enabled, because I'm using A and B outputs, ports. So A is that first bit, B is the second. So to enable those two bits, the hex would look like 3, right? That nibble as a hex digit is 2 to the 0, which is 1, plus 2 to the first, which is 2. So 1 plus 2 is 3 in hex. So that value, now I've updated the value in R2 to turn those two bits on with an OR, and then I store that value back in the clock enable register. So now the A and B output pins are enabled. Okay. So I'm still just kind of working my way down to numbered items. That was number 3 that I filled in. So the A modes have already been set for me. You might recognize that value from earlier. So this whole section goes all together. We load the address of the A mode register into R2. I don't know why I switched it, but anyway, we load the address of the mode register into R2. We load the value into R3. It kind of bugs me that those are in that order, but it doesn't really matter. So now R3 is the value that needs to be updated. So we get our bit manipulating value into R4. We OR that in here. Since the first two are the same, I can just eliminate one of them, by the way. And then I'm going to store the R3 back into R2, which is the mode register. I don't know why I switched the numbers up, but it doesn't really matter. You just need to pay attention to what's going on. But I didn't really have to do anything there. It was already done for me. Okay, so now we need to do the B mode register to make sure that the appropriate B pins are set. So mode is 2 bits per pin. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. Let's see, I need B8, B9, B10, and B6. All right, so 6, 8, 9, and 10. So I don't care about 0. I don't care about, that's pin 0, those 2 bits, mode. Here's pin 1, don't care about it. Pin 2, don't care about it. Pin 3, don't care about it. Pin 4, don't care about it. Pin 5, don't care about it. Pin 6, I do care about, and to do output on B6, I need the 0, 1 value, which you probably recognize. So that's B6, B0, B1, B2, B3, B4, B5, 2 pins at a time, B6. I don't care about 7. I do care about 8. I do care about 9. And I do care about 10. I do not care about 11, and once I finish that nibble, I don't need to go any higher. So I need to translate this now, and please double check me, everybody, to make sure I don't make a mistake. Since this is more than 4 nibbles, I have to use the pseudo instruction here. All right, so this one's 1. This one is 5, I hope. This one's 1. And then 3 zeros. So a 0, a 0, a 0. So 1, 2, 3, 4, 5, 6 nibbles had to be translated into hex. 151,000. So that is the value I will use now to update the B mode register so that I can do outputs on B pins. The OR has already been done for me. So the OR updates R5 with my bit manipulating value, and then the store writes that value back into the mode register, so now we can do outputs on the pins that we want to do outputs on. Okay, so let's see what else is going on here. That's number 4. So I'm just paying attention here. R2 is the address of the A bank. R4 is the address of the B bank, so I'm just sort of watching that. R6 is being used as a counter. So it's starting at 127. That's 127 in hex. You could, of course, write it as decimal. Same difference. So R6 is a counter. So what the purpose of this circuit is to actually display the value in R6 as binary using our LEDs. R6, R7. So R7 is a up or down flag. So the values, because they're only 8-bit signed values, we can only go as high as 127 and we can only go as low as negative 128. So when R7 is 0, we're counting down 127, 126. When R7 is 1, we're counting back up. So this is what will allow us to stop at negative 128 and turn around and go back up to 127 and then stop at 127 and turn around and go the other direction. We're going to have to write logic to do that. Okay, so it's telling me in number 5 to bit clear in R3. So, and it also tells me that R3 is the A bits. So I need to use a bit clear on R3 with a value. We'll see if this works the way we want it. Yeah, it's going to work. We're going to bit clear with the value to clear the GPIO A bits. So I need to go, that's 1 bit per for the outputs part. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So now I need to go remind myself what, which A ones we're using, which is 5, 6, 7, 8, and 9. So A 5, 6, 7, 8, and 9. And right here. Line 95. 5, 6, 7, 8, and 9. So I don't care about 0 or 1 or 2 or 3 or 4. I do care about 5 and 6 and 7 and 8 and 9. And then I'll finish that nibble. So those are the bits I need to clear to zero out all the outputs that are on the A bank. In hex, that looks like 3 E0. You've probably seen that value before. And then that value is being stored back. So I'm being told that R3 is where I do updates for the A bank. So that's what I did. I just did updates on R3 for the A bank, and then that value is stored back into memory wherever R2 is, but I remember from above on line 78 that R2 is in fact the A bank, so confirm that. I need to bit clear R5 for the B bank. So bit clear R5, and then I need to figure out what bits on the B bank. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 1 bit per down here. Let's see, B was 8, 9, 6, 8, 9, and 10. 6, 8, 9, and 10. So not 0, not 1, not 2, not 3, not 4, not 5. I need 6, not 7. I need 8, 9, 10. And then I'll finish that nibble and we're all done. And then translate that into hex. So this is, what is that? 1 plus 2 plus 4 is 7. 4 and 0. Check me on my binary to hex. If you see a mistake, please let me know in chat. All that code really does is just every time we go in the main loop, we clear out the display so that nothing's lit up. That's all that code is meant to do. Have a little pause loop here, which is in a slightly different place. So we actually have 2 delay loops in this program. Don't get thrown off by it, but there's nothing to do here. It's just telling me there's a small pause before the next thing happens as the program's running. Okay, so now we're getting to some hard stuff. So before we do that, let's just turn all the lights on and see what happens. So the trick here, and I'm cheating because I wrote the lab, the trick here is to remember where I turn all the lights on at. I know from looking down here at line 132, that's where I'm at right now anyway, R3 has the value for the A pins, and R5 has the value for the B pins. So to do a test, I'm going to turn everything on first. And what's nice about this, and to do that I'm just going to OR. So I'm going to OR R3 with the value. Turning everything off in R3, which is where the A pins are, or turning everything on is the same value as turning everything off that I did on line 96. So those same bits that I cleared on line 96, I'm going to turn on line 132. And then I'm going to do the same thing for the B pins, which are, that value goes in R5. The same value that I used to turn them all off up here, that's for me on line 103, is the same value I will use to turn them all on. This is just a test to see if I can get the whole bank blinking on and off. Okay, so I'm going to hit pause just to see if anyone needs me. I might be going a bit fast for you to do it in real time, so hopefully you'll make use of the video if you need to be able to stop and rewind it and slow things down a little bit. So this is not really part of the lab, this test that I'm doing. I just want to see if my circuit's functioning correctly. I don't think I have to do anything else. So I just sort of added right here before show bits, which for me was on lines 136 and 137. I'm just going to flick everything on. And if the program works correctly, then as it runs, it's going to, here's the main loop. It's going to turn everything off and then delay and then turn everything on and then delay and then repeat. Turn everything off, delay, turn everything on, delay, turn everything off, delay, turn everything on, delay. That's what I want it to do. Okay. I'm going to bring the browser back up for a second because I want to show you that the recipe has changed. So this week is the first week where we stop using OpenOCD anymore. So we're still going to compile the code. We're still going to produce the ELF file like we did before. But then we're going to produce a new file called a bin file. And then we're going to use a new piece of software called STFlash to directly burn the software onto the board. So no OpenOCD anymore. We're just going to flash the program onto the board and run it. So no stepping, no inspecting registers. We're just going to flash the program onto the board and run it. So I'm going to do these steps, hopefully without any errors, but I've been writing code for a while, so we'll see. So far, so good. So I did the compile step. I'm going to do the ELF file step. So far, so good. I'm going to do the object or the bin file step. So far, so good. I need to plug in my board. It's going to be running old software, so it might look like chaos for a little bit, but I need to power up the board for the flash part. So make sure that you're plugged in before you flash it, because if it's not powered, you can't flash it. So it's doing lab 9 in a weird location. That's fine. Okay, so no OpenOCD. I'm just going to flash it. So what's going to happen is it's going to take that bin file I just made and burn it directly on the board. No. I already did that step. I think I copied it. Yeah, so there's the flash step. Okay, so usually after the flash step, which is what I'm going to have to do, so notice nothing's happening. Usually after the flash step, you have to press the black button to reset and start the board running. So when I do this, press the black button, what should happen is the whole board should start flashing on and off, or I made a mistake somewhere. Okay, and all of the lights, that's just a test to see that my circuit is in fact wired up correctly. It's not yet doing what we want it to do. But it's a good start. So now I'm using a whole new set of outputs, the B pins, whereas before I was only using the A pins. And I've got all that stuff wired up, and I've got a piece of software running on it that just flashes the entire bank. That one that looks blue to you is red. Or is it? No, it is. It just doesn't look that way to you. And then that sickly greenish yellow is a gorgeous green for me. Well, green, but not sickly. Okay. So we have time to start, and then probably, well, let's just see how far we get with the time that we have left. But what we may do is I may sort of extend this out to next week. We'll find out how far we get. Does anyone have questions for me before I go back into the software? Hopefully you were able to follow along okay. All right, so we're going to do some new stuff here. This is stuff that you haven't done before, but you have heard of it before. So the whole point of this circuit is to make these lights blink, showing a counter value. So when the value is 1, we just want this one light on. When it's 2, we want just this one light on. When it's 3, we want both of these lights on, and so on. So this will be a binary display of our R6 counter value. And then this, what looks blue to you, but what is actually red, that will come on when R6 is negative. That's what we want to do. So let's try it out. And we're going to cheat a little bit, and I'll show you what I mean by cheating. Because it's fairly easy to get yourself sort of neck deep before you have anything working. So I'm going to change something to start. Is the counter being moved? It's not. Okay. So let's, how do we want to do this? I'm going to go to line 85. And I'm just going to, for now, temporarily I'm going to make that 1. Because I want to see if I can make 1 show up in binary first. So temporarily, I'm going to make my counter on line 85, for me on line 85, just be the value 1 instead of 127. Change this back to 127 later. Because I want to see if I can just make the binary value, a binary display for 1 show up, which should be just 1 LED. Hold on there. They're not all perfect and straight. That's a little better. Okay. And then I'll probably try -1 after that. Okay. So now I'm going to scroll down. So I'm down here on line, on number 7, which for me is on line 118. So it's roughly probably where yours is at. So to do this, I can't just compare for values. I can't, it would be impractical for me to compare R6 with all of the values from -128 to 127. I'd be writing comparisons for a year if I were to do that, right? It's 255 different values. So a far more efficient way to see which bits in R6 are on is to do a bit testing instruction, which is what the TST instruction does. It allows me to test individual bits. So I'm just going to start by testing bit 0 in R6. Hold on, I got to deal with a distraction real quick. Okay, so you have to imagine R6 has a value between -128 and 127. That's the range of signed integers. We're only worried about 8-bit values right now because our display is only 8 bits. So we're going to sort of purposely make sure that R6 can never be anything outside of -128 to 127. So what that means is we only have to worry about 8 bits. And when R6 is 1, the bits look like this. So the way I'm going to write this code is I'm going to test these bits. And if that bit is on, it has a value in it, then I'm going to turn on an LED that's associated with it. So the way we do this is the test instruction. You could do it uppercase, but I don't. R6 has our value, and we're looking at that first bit. I usually do it in hex. That's that first bit right here. That's the one I want to test. It could be that all these others are also turned on right now, but that doesn't matter to me. I just want to know, is that first bit set? All right, and now we're going to do one of the things that is cool about ARM assembly. It has an instruction called if-then, which is kind of like writing an if statement. Now this part, the second part of this, is not intuitive, but you can write kind of if-then instructions. And the counterintuitive part about this if-then is that a successful test on a bit yields a not equal. There is a reason for this that we could work our way through mentally, but just sort of for now get used to this idea. I'm testing the bit right here in R6. I don't care about what any of the other bits are doing. I just care about, does that bit have a 1 on it? And then this is if, the IT literally means if then. If it's set, which unfortunately looks like not equal, but that means that bit is in fact set, which is counterintuitive. So that tells me that the 1 bit is set. And then I say, let me move this over. so it's just easier to read. That's kind of like an if statement in ARM assembly. So we test a specific bit. If that bit is set, then we OR something when that bit is set. This is just how ARM works. This NE right here is connected to this NE right here. So this is how you do an if-then statement in ARM assembly. So those three things go all together. I'm testing a specific bit. If I found the bit was set, then I'm going to OR something when the bit was set. Let's see, what do I want to OR here? A is in R3, isn't it? Yeah, A is in R3. This is the tricky part, because what I want to OR is my A5 bit. That's the LED representing that part of the value. So if you can kind of imagine these 8 bits are being represented by 8 LEDs, you'll get used to it. Feels really, really funny at first. So let's see. I need to turn on A5. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I don't need 0, 1, 2, or 3. I don't need 4. I do need 5. So I'm going to turn on bit 20. So I appreciate that this is going to take a while to get comfortable with. Those 3 lines represent me looking at the value in R6 and asking the question, is that first bit in R6 flicked on? That's it. If it is, then I'm going to enable an LED that I'm going to use to correspond to that bit, which for me is the A5 LED, which should be for you as well. So if that bit and that value is set, then I'm going to turn on my A5 LED because I want my LEDs to represent that R6 value, what it would look like in binary. I'm going to go comment out my testing section here. I don't want everything coming on anymore. I just want to know if I can turn one on. So in theory, if I make R6 be 1 and just leave it there, then that A5, which maps to that bit, should come on, go off, come on, go off, come on, go off, because the counter is always 1. Okay, so I'm going to save that. What are you looking at right now on my screen? Okay, so now I'm going to go back through the whole process here. I'm just going to use the up arrow, so I'm going to recompile first. Then I'm going to make the elf file. Then I'm going to make the bin file. Then I'm going to flash the board. And then I'm going to press the black button to reset. And what you should be seeing, hopefully you see it, there it is. So that's no magic. The reason why that light is coming on is because I programmed it to. I programmed that light to come on when a particular bit in R6 has a value in it. Okay, so I'm going to make this value be 3. So I'm going to go back up to line 85. I'm going to make this value be 3. And then I'm going to go down below and just sort of show you what does 3 look like in binary. So if all right, so I changed line 85 to move 3 into R6. Eventually I'm going to put it back to 127. 3 in R6. So now I'm going to scroll back down to where I was fooling around, which for me is on line 126 or so. So when the value in R6 is 3, those 2 bits would be set. So I still want to turn on A5 because that bit's still turned on. But now I also want to add a new bit test in R6 to check that second one, which is bit 2. So I'm checking the second bit over, the 2 to the first bit, to see if that's turned on, which if R6 is 3, it will be. Then I do if then not equal, because that's how you check for a successful bit test. And then or not equal. R3 again, because that second bit is a 6. So this value will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I don't care about those. 1, 0, 1, 2, 3, 4, 5, 6. So it takes a lot of mental gymnastics. So that value is going to be 40. 0x 40. So I'm checking bits in R6, and I'm using basically the value in R6 at the binary level to decide which of my LEDs to turn on. So if the value is 3, then my first 2 LEDs on my board should turn on. So now I'm going to go back and I'm going to go through the whole process again. So compile, elf file, bin file, flash the board. And then I'm going to press the black button to reset the circuit. And what should be happening, since the R6 value is stuck on 3 right now, is the first 2 lights come on. I can't decide. I think what I'm inclined to do is carry this over to next week. That would give you a chance, if you're so inclined, to sort of play around and see if you can get more of this going. So notice how I did this. So I'll show you where I'm going to pick up next time. Let me put a note here. So homework 9. Hopefully I'm right that it's homework 9. Yeah. So we're going to push the lab until next week so that we can spend a little bit more time together on it. What's today, April 9th? So this week is only homework 9. We'll complete lab 10 together next week. And then it should be fairly easy to get lab 11 finished next week as well. So lab 10 will be due next week. For this week, it's only homework 9. Hopefully this, if you are interested, this gives you some space to see how much more you can add. I will tell you, though, that the next thing that I would do is I would change R6 to have this bit on, which if I did that, that is, what, 7? And then I would just keep sort of working my way up. I would change this counter to add another bit on it, and then I would add another test, which I'm going to do, just my closing thought. So I'm worried about this bit, which is at the 4 position in hex. That's a successful bit test. And then we need to change R3's value with R3 maps to, so bit 0 is A5, bit 1 is A6. So here's, I'm on 2 squared bit right now. That's A7, which is 40. That's 2 to the 7th. So I know you're sort of having to do 2 binary values here. R6 is binary value you have to worry about, and R3's binary value. R6 is just a counter. R3 is where you're turning that counter into a binary display. Yes, 80, thank you. Good catch, thank you. 80. At which point the first 3 should come on. So let's close the video down by doing that one. You can probably see where this goes. So if you want to take that as far as you want to, you can finish number 7 for yourself. But I will finish number 7 at the start of class on Tuesday next week, and then we'll do numbers 8 and 9, which aren't hard. So now you have a sense of what to look at when you're doing the homework questions, which hopefully you're doing just so you know what's going on in advance. Let me go through the process real quick and make sure that, in fact, that makes my first 3. So compile, elf file, bin file, flash the board. And then black button to reset, make the circuit run. And there's the first 3 coming on. So what my display is showing me, if I know binary, is that my counter R6 has the value 7 in it right now. What's going to happen eventually is if it were -7, that light comes on to say, hey, this is negative. But you may know that -7 looks different in 2's complement, so -7 is going to look funny anyway. But that's +7. This light is off, which is our negative indicator. This is binary +7, right? These are all zeros, and then these bits would be set for 7. So if it were 8, only that one comes on. If it were 9, those 2 come on, and so on. That's actually pretty fun. I could keep going, but I sort of tell you that I'm only going to go for an hour, so I'm going to stop, and then we'll finish next week. So does anybody have any questions for me? All right, thank you too. Hope that made some kind of sense. Just be patient, give it some time to sink in. Where it just feels funny at first because we're taking a counter value from a register and we are writing a program that will show a binary display of that value. That's what we're doing. This is how they make binary clocks. If you've ever seen one, they just take values from the register and then they map it onto LEDs to present a binary display. Okay, so I will see everybody on Tuesday morning at 8:30. You can always email me if you have questions. So if you can get the word out, homework 9, we will finish lab 10 first thing on Tuesday morning, and going into the homework questions. So this will go a little bit faster, but I want to take time on this one because once you get this sort of what are we doing with our circuit idea down, then everything else for the rest of the semester I think comes a lot easier. So we'll finish the display. We'll add in the ability to count R6 up and down so the display actually changes over time. And then we'll also add in the ability to stop at -128, turn around and start counting back up. which will be kind of fun, and it will show off some of the things that are awesome about arm assembly. So everybody have a good weekend.